Another way that we can be asked questions on the rectangular distribution is where we are giving it as a description with the words rectangular distribution and the interval of which our values are there. We can have to go from this to the probability density function, which is what was in the first part of our notes. If I go back, this was our probability density function here. So we are now trying to go from a description to the probability density function. So the probability density function would be f of x and then a curled bracket like this. We know that our x values are going from 97.5. Now, because these are square brackets, that means that it can take on those values, so it's going to be less than or equal to. If instead it had curved brackets, so if it was written like this instead, then we would have strict inequalities, so our inequality symbols would look like this instead. But because we have square brackets, it means it can take on those values. So less than or equal to x, and again square brackets at the end, so less than or equal to 102.5. Now, in order to decide what probability is being taken on between those two values, remember that that's going to be 1 divided by b minus a, so 102.5 minus 97.5, which gives us a fifth. So our probability here is a fifth between those two values. And don't forget the second line of the probability density function, which is really important to let people know that it's going to be 0 otherwise, which means everywhere apart from inside that interval has a 0 probability of happening, so it's 0 otherwise. Part 2 of this question, we're asked to find the standard deviation. So remember that we have to start off with the variance, which we're not given the formula for, which is going to be 1/12 of b, 102.5, minus a, so minus 97.5 squared, which gives us 25/12. And remember that that's for the variance. So we're asked for the standard deviation. So the standard deviation is going to be the square root of our 25/12, which I've already put into my calculator earlier on, which gives us 1.44 to 3 significant figures. Now we have a car chosen at random from a speed recorded as 100 kilometers, because remember here, this is what we were looking at. So this is the exact speed of cars that were recorded at 100 kilometers per hour. Their actual speed is between these two. So we're trying to find the probability that the exact speed is between 98 and 101 kilometers per hour. So the best way to do this one is to give ourselves a little diagram like we did with the other questions. So we're going to have our rectangle, which remember has a height of a fifth and is going between 97.5 and 102.5. And this is where we shade in the area that we're actually interested in. So we were looking at between 98 and 101 kilometers per hour. So we're looking at between 98 and 101. So we're looking at this area here. So the width of that area is 3 and the height is a fifth. So our probability is 3/5. And if we wanted to write that as an actual, using the probability notation that we have, it would be the probability that 98 is less than x is less than 101. and we can put those as equal to signs. Remember, it doesn't matter because this is a continuous function, which means the probability of x taking on any singular value is 0. So if we were given an extra part to this question that isn't on here, let's call it II, BII, what's the probability that x is equal to 99? It would be 0. If we were given III, the probability that x was exactly equal to 100, that would also take on 0. So the probability that it equals exactly any value is going to be 0 for the rectangular distribution. Now, usually in an exam style question which has the rectangular distribution, the last part of it will go on to something else. So it might be using some knowledge that you already have from different topics in statistics. So here we have a random sample of 50 cars, each travelling at a speed of which is recorded as 100 kilometers per hour, and the mean speed is denoted as this. So we have a sample of 50. We're talking about the mean speed. So this is screaming to use central limit theorem here. So we're trying to specify fully a distribution which may be used to model the variable x bar given a reason for your chosen distribution. So this sounds like it's going to be using central limit theorem, so it's going to be the normal distribution. So we have to remember that central limit theorem states that if we're talking about the means of the sample and our sample is sufficiently large, which we have here because our n is 50, which is more than 30, the mean of the sample is going to be the same. So the mean is still going to be the same as what it was before. Just to double check that, our E of x, our mean, would have been a half of A plus B, 97.5, plus 102.5, which does give us 100, which we would expect because we're looking at values that are around 100 kilometers per hour. So our mean is still 100. But the central limit theorem also states that the standard deviation of the means is going to be the same as the standard deviation of the population, which was our 1.44, divided by the square root of our sample size. So we have to remember that this part here is the variance, so we're going to have to square it. So it's going to be 1.44 divided by the square root of 50 squared, and then we're going to close our brackets. So that is our distribution. If we're trying to give a reason for our choice of distribution, we can say due to central limit theorem, we know that the means of the samples will be normally distributed with the same mean as the population and the standard deviation divided by the square root of n. Now, the reason why we don't need the population to also be normally distributed is because our sample is sufficiently large. So we can add that in here. It's only worth 3 marks, so you probably wouldn't have to go into this much detail, but you can say that the population distribution is irrelevant. as the sample is sufficiently large, more than 30. Now, obviously, a downside to this general rule of having more than 30 being a sufficiently large sample is if you think about the actual population of things, sometimes 30 would not be a large sample. For instance, if we had a question which was on about the population of the United States of America, then having a sample of 30 people and saying that that is representative of the entire population is a bit silly. Okay, so that sample size being more than 30 does have its downsides in real life applications. It won't always work. Okay, so that's how we would answer a question if instead of being given the probability density function, we were given a description of the function using this notation here or with the curved brackets. Thank you very much.